Having done this, we can now load this configuration file in SUMO and run the simulation. We load SUMO GUI and open simulation to browse and select the created configuration file. We perform a few settings for better visualization. We increase the delay to visualize the vehicle movement. If we don't do this, the simulation will end very fast. We also set the vehicle shape and size. As you can see, once simulation starts, vehicles are moving in the road network created based on the trips that we have generated. At the junctions, the vehicles stop and proceed based on the traffic signal. Similarly, you can also generate vehicular demand for any network regardless of whether it was created using NetEdit, OpenStreetMaps or any other tool. As mentioned earlier, NetSim GUI takes a SUMO configuration file as input and recreates the SUMO network configuration in its simulation environment. NetSim then allows users to configure various protocol parameters in the vehicle properties. NetSim GUI uses inbuilt applications dedicated for VANETs to load the road network configuration with the help of road placement and device placement logs. As you can see here, creating a VANET network in NetSim can be effortlessly done by simply providing a SUMO configuration file as input. Users can load a SUMO configuration file in NetSim by clicking on New Simulation menu item and then selecting the VANET tile. This prompts the user to provide a SUMO configuration file as input. Once the configuration file is provided, NetSim automatically takes care of making internal calls to SUMO and loading an equivalent of the SUMO configuration in the NetSim GUI. The first option for coupling NetSim and SUMO is the offline coupling mode. Here, SUMO is used to model the vehicular movements in roads considering signals, lanes, etc. This realistic movement of vehicles is saved into a trace file. The trace file is converted per NetSim's node mobility file format and fed as input to NetSim before the start of simulation. NetSim then simulates the communication networking protocols and outputs the performance metrics, traces and logs. This method of coupling NetSim and SUMO is simple and easy to perform. The trade-off is that there is no data sent back from NetSim to SUMO, and there is no runtime interaction between NetSim and SUMO. In case of offline coupling, a VANET network in NetSim needs to be created by manually dropping the nodes at specific locations as per the SUMO configuration and establishing connection between them. Further, file-based mobility input has to be provided for introducing vehicular mobility as per the SUMO configuration. The SUMO trace XML file generated from the SUMO network is then converted per NetSim's mobility file format. The format is simple. It has timestamp, vehicle ID, and the respective X, Y, and Z coordinates. Thus, the mobility is modeled by taking into account the positions of vehicles with respect to time. SUMO and NetSim animations are shown side by side here. To the left is the SUMO network with roads, junctions, and traffic signals with vehicles moving. To the right is NetSim showing BSM packets broadcast from one of the vehicles. The vehicle mobility in SUMO is replicated in NetSim as it uses SUMO's mobility trace as an input. Packet delivery ratio or PDR is a commonly used metric to analyze the performance of vehicular communication. It is defined as the probability that a vehicle can successfully receive a packet from a broadcasting entity. As a toy example, two cases are considered. In case 1, one vehicle 1 broadcasts basic safety messages at a rate of 50 packets per second. In the second case, two vehicles, vehicle 1 and vehicle 2, broadcast BSM messages at a rate of 50 packets per second. In case 1, vehicle 1 is broadcasting BSM messages. Vehicle 4 is closest to vehicle 1, followed by vehicle 3, 5 and 2 respectively. As simulation progresses, inter-vehicle distance changes due to mobility. We tabulate the PDR for broadcast transmissions from vehicle 1 to the other 4 vehicles. We observe that the vehicles that were closer to vehicle 1 on average see a higher PDR than the vehicles that were further away. This is as expected. Further away nodes see lower signal strength due to path loss and hence higher error rates. In case 2, vehicle 4 also broadcasts BSM messages in addition to vehicle 1. Comparing table 1 and table 2, we observe that the PDR of packets sent by vehicle 1 to vehicle 2, 3 and 5 drops by nearly 10%. This is due to interference from vehicle 4 transmissions. To summarize, in this toy example, we set up a realistic scenario with roads and vehicles. Then we simulated safety message transmissions and saw how wireless communication effects such as path loss and interference impact the transmission of messages. We will now look at one-way coupling and then move to two-way coupling. In this method, there is continuous data transfer from SUMO to NetSim throughout the simulation. However, there is no feedback going from NetSim to SUMO to alter the network behavior during runtime. Interaction with SUMO during runtime is made possible with TraCI APIs. Giving access to a running road traffic simulation, it allows to retrieve values of simulated objects and to manipulate their behavior online. It uses a TCP-based client-server architecture to provide access to SUMO. NetSim uses TraCI commands to step simulations and to retrieve the vehicle position coordinates periodically, eliminating the need to create traces prior to simulation. Based on the position coordinates returned by SUMO, the position of vehicles in NetSim are updated at runtime. You can now see how easy it is to perform VANET simulations in NetSim using NetSim SUMO one-way online coupling. NetSim allows SUMO configurations to be directly imported. It automatically detects vehicles, roads, lanes and junctions in SUMO network and replicates it in NetSim GUI. Users need not manually place vehicles nor establish connections between them. And there is no need to generate or provide trace files as input to NetSim. All this is automatically fetched during runtime. Upon running simulations, NetSim and SUMO simulations run in parallel and are synchronized in time. TraCI permits controlling the behavior of vehicles during simulation runtime and can be used to better understand the influence of VANET applications on traffic patterns. It allows modifying the state of traffic objects such as vehicle information, route information, infrastructure objects such as traffic lights, bus stops, charging stations, etc., network objects such as lanes, junctions during runtime. Simulation, therefore, does not follow a predefined pattern. Road traffic behavior gets altered in runtime using a feedback loop from NetSim to SUMO using TraCI. This makes the simulations more realistic since the network topology of vehicle-to-vehicle communication now changes with feedback. As you can imagine, controlling the mobility of each simulated vehicle allows modeling more realistic driving behavior. Simulations would therefore closely parallel real-world working. TraCI commands are available for simulation control, object value retrieval, object state change, subscriptions, and accessing generic parameters from SUMO. For example, stepping the simulation, closing the simulation, etc. are associated with simulation control. Getting the speed, angle, position, etc. of a vehicle are associated with value retrieval commands. Setting the vehicle speed, triggering slowdown, setting traffic signal phase duration, etc. are associated with state change commands. As an example, we'll now look at the dynamic traffic signal control which uses NetSim SUMO two-way coupling. This project is available in NetSim File Exchange with source codes and documentation. Our File Exchange link will be given at the last slide of this webinar. In this example, we consider a simple road traffic network with a junction having a traffic signal in SUMO. The equivalent network in NetSim has an RSU at the junction which is responsible for dynamic traffic light control. In the road network, the north-south lane is the emergency lane and the east-west lane is the regular lane. There are no left or right turns permitted. The RSU is responsible for ensuring uninterrupted traffic flow in the emergency lane. This is achieved by identifying vehicle type, distance, priority, etc. of the vehicles approaching the junction from the periodic beacons it receives from the vehicles. This is modeled with V2I communication support in NetSim along with feedback loop established with SUMO. There are 4 traffic light signals and 4 phases defined to determine the color of the light at each signal. In phase 0, a north-south lane with signal IDs 0 and 1 has green light and east-west lane with signal IDs 1 and 3 has red light for a duration of 10 seconds. In phase 1, north-south lane with signal IDs 0 and 2 has yellow light and east-west lane with signal IDs 1 and 3 has red light for a duration of 6 seconds. In phase 2, north-south lane with signal IDs 0 and 2 has red light, and east-west lane with signal IDs 1 and 3 has green light for a duration of 31 seconds. Finally, in phase 3, north-south lane with signal IDs 0 and 2 has red light, and east-west lane with signal IDs 1 and 3 has yellow light for a duration of 6 seconds. Shown here are how the signal switches from phase 0 to 1 to 2 to 3 and back to phase 0 with the lights set in each signal for the phase definition and duration. The time field in the SUMO GUI displays the time in seconds as simulation progresses. The tracker window shows the current state of the traffic signal with the phase and signal color. Phase 0 lasts for 10 seconds, during which the signal remains green in NS lane and red in the EW lane. At the 10th second, the signal shifts to phase 1, during which the NS lane switches to yellow and the EW lane switches to red. This phase lasts for 6 seconds, and at the 16th second, the signal shifts to phase 2, during which the NS lane switches to red and the EW lane switches to green. This phase is the longest and lasts for about 31 seconds. At the 46th second, the signal shifts to phase 3, which lasts for 6 seconds, during which it switches to yellow in the EW lane and remains at red in the NS lane. The cycle again continues by shifting to phase 0 at the 52nd second. This is how the signal normally behaves without any feedback or control. Suitable code modifications are done in NetSim to modify signal behavior based on distance between the junction and an approaching emergency vehicle. One option would be to switch the NS lane used by the emergency vehicle to green at some point. A better option is to precisely measure the distance of the emergency vehicle from the signal and then first keep the EW lane green to prevent vehicle pile in that lane. And then at exactly the right moment switch the NS lane to green for the emergency vehicle to pass by. This is possible because we can process the vehicular data collected by the RSU that is near the signal. With this code change, we see that when emergency vehicle is at some distance d1 away from the junction, the EW lane switches to phase 2 with green to clear traffic. Next, when the emergency vehicle is at a close distance d2, the signal switches to phase 3 with yellow light in the EW lane to alert vehicles in that lane to halt. After this, the signal appropriately switches to phase 0 with green light in the NS lane and red light in the EW lane, ensuring free flow of the emergency vehicle and preventing any imminent collisions. This example shows how vehicular traffic flow changes in runtime with V2V and V2X communications. This was made possible by interfacing NetSim with SUMO using two-way coupling. This example shows how vehicular traffic flow changes in runtime with V2V and V2X communication. This was made possible by interfacing NetSim with SUMO using two-way coupling. There are several VANET R&D examples and research publications done using NetSim. Some of the interesting examples and reference links are provided here. Notable examples include dynamic traffic light control, which we discussed now, followed by the sinkhole attack project, IDS project, broadcast packet dissemination, and autonomous vehicle speed control. With this, we have come to the end of this webinar, and we'll now have a Q&A session.